Okay, so I'm going to go over a few of the problems on this assignment. First off, describe the end behavior of the polynomial function, and then the possible zeros and the possible positive and negative zeros. So the main thing here I want to start off with is just what is this end behavior thing? Because you kind of need to know what that is and how to find that for obviously these and then for these graphs later on. Now, it's real simple to find this quote-unquote end behavior. You just need to understand that it's essentially the shape. All polynomial graphs fall into one of four possible shapes. They either go up to the right and up to the left, down to the right and down to the left, up to the right and down to the left, or up to the left and down to the right. If you think about it, these are the only four combinations that you can do as far as arrows when you're going off to the right or going off to the left. At least I should say these are the only four combinations that polynomials will do. Now, which of these four shapes it's going to have is dependent on just two features of the polynomial. One is the degree, which is the highest power of x. So the degree here is, I'll put d for degree, that's 4, whereas the degree here, for instance, that degree is 5. And you can see what the degrees of these other ones are. This one's in a non-standard form, so its degree is also 4. And this one's tricky because it's factored. So it's I'll talk about these in a second. But just for these first three, I guess you can just see that these are 4, 5, and 4 respectively. All you need to observe about the degree is whether or not that degree is even or odd. If the degree is even, then the shape of the polynomial will be one of these two shapes, the top two. They either both point up or both point down. If the degree is odd, it's one of these two shapes, where it either points up to the right and down to the left, or up to the left and down to the right. Now, how do you tell, once you know if it's even or odd, which of the two variants it is? Well, that just comes down to the leading coefficient, or the coefficient of that highest power of x. So for this first one, the leading coefficient would just be 1. For this one, the leading coefficient's -2. For this one, it might be weird. It's not -2, actually. It's this -1, because that's the coefficient of the highest power of x. But at any rate, all you need to know for the leading coefficient is if that number is either positive or negative. If you're positive and you're even, then you're this shape. If you're positive and odd, you're this shape. If you're negative and even, you're this shape. If you're negative and odd, you're this shape. And you can look this kind of stuff up online, the end behaviors. There's 4 possible shapes to it. But at any rate, you can describe the end behavior for each of these. And later on with the graphs, they have you kind of do it here. They say end behavior. And you can describe this in terms of like just arrows, or you could just say like up, up. Like for instance, I'll tell you this one is one of the ones that's up, up. You can describe it in words here, or you could use the proper notation with like x's and infinities. But I won't go into that now for the sake of time. I'll just say that's end behavior. As far as finding possible zeros, give me a second, I need to clear this up because this will take some more space. As far as finding possible zeros, this is a little theorem called the rational zeros theorem. What it says is that all the possible rational zeros can be written as plus or minus p over q, where p represents any possible factor of the constant term, and q is any possible factor of the leading coefficient. So in this case, the plus or minus p over q would be all the factors of 5, which would just be 5 and 1, over all the possible factors of 1, which of course is just 1. So it's 5 over 1 and 1 over 1. You add in the plus or minus, and these are your possible real zeros. The possible positive and negative zeros is another thing. It has to do with counting how many sign changes there are as you count along this polynomial. And honestly, for the sake of time, I just don't want to go into that right now. We'll talk about the graph, so I don't have much time here to explain this. So I'll just say that you can look this up. There's a sign changing rule for how many positive and negatives you have. If you don't get this exact thing, it's actually not the biggest deal. Like, actually, in the grand scheme of things, it's not essential. It just helps you speed up some parts of algebra. The main thing, though, is how to find all the possible rational zeros. I'll just real quickly throw out for this one, because this one's a little more complex. You would put the possible factors of 12, which are 12, 6, 4, 3, 2, and 1. And you have to put those all over the possible factors of 2. Now, I know it's a negative 2, but since we're plus minusing all these, it doesn't really matter if it's positive or negative. They're all going to come out as positive or negative in the end anyway. Now you might think, okay, so I'll put these all over 2, right? And that's true. But you have to put all the factors of 12 over all the factors of 2. 2 is just one factor of 2. The other factor of 2 is 1. So you have a whole second set of 12, 6, 4, 3, 2, and 1. But these would all be over 1. Just pretend to put plus minus in all these. But yeah, it's a lot of possible zeros. Okay, that's just the first part there. Real fast now on kind of these, because what are these? And how you do the majority of these problems. But at the end, they start turning back into non-factored polynomials. So I'll speak about these beginning ones at least. So you can at least do these. If the polynomial is already in this what's called factored form, you still can figure out the end behavior and the degree, which is important for figuring out the end behavior. You just kind of have to use your imagination. In theory, you could just multiply these two polynomials together, these two binomials together. And, for this one, it's easy. For this one, a little harder, but doable. But the truth is, you don't have to do it for any of these. You could just look at how many x's there are and foresee what the power of x would be if these are all multiplied together. You foiled this whole thing out. Ultimately, the highest power of x would be 1x times 1x. So you'd have x squared come out of that. Maybe x squared plus or minus something, something, something. But all that matters is that the highest power is 2. It's a degree 2 polynomial. But beyond that, you can see that these two x's are both positive. So the leading coefficient, whatever it is, in this case that'll be 1, will be positive. Positive and even, from what I showed earlier, is going to be the end behavior at points up in both directions. So already when I'm sketching my graph, I've got a pretty good picture of what it looks like. This is why I draw the end behaviors going up to the left. That's what it's saying there. It's up left, and up right. Lastly, the zeros. Now, this is easy when it's in this factored form. You just have to find what makes this factor equal to 0. Well, that would be a positive 1. And what makes this factor equal to 0? That would be a negative 2. So these are the two possible zeros. You could plot those roughly. One at say 1, and one at say negative 2. And if you just kind of connect the dots, almost like you're just weaving a line through a thread, did the best job of that one. Try that again. Yeah, something like that. Not the best depiction, but something along these lines. You got a pretty accurate sketch of the graph. You cross through with the zeros, you have the right end behavior, that's about it. Last part is that y-intercept. And again, I'll say this is a very minor thing to calculate. You can find it by just plugging in 0 for all the x's, because the y-intercept is when x equals 0. So you put 0 in for x here, 0 in for x here, you'll have negative 1 times 2, which is negative 2. So it technically crosses at negative 2, as I've roughly depicted, but not a big deal. But yeah, just one more as an example there. So this thing's degree would be, well, I got 1x times x minus 3, but this thing is squared, so there's going to be 2 x's that come out of that, and then there's another x. There will be 4 x's in this total. The highest power will be x to the 4th. So my degree is 4. That's, again, even. All of these x's are positive. Like, there might be a negative 3 here, but all the x's are positive, so I'm expecting this to be a positive even again. They'll have the same end behavior as the last. They'll point up in both directions. Zeros will make each of these factors equal to 0. So you'll have a, say, negative 4. We're going to go right to left this time. Negative 4 from this one. Positive 3 would make this one 0. And everyone always forgets this one. What makes x equal to 0? Well, just 0 itself. Y-intercept is also pretty boring. Whenever 0 is an x-intercept, that means the y-intercept is also 0. Because what would make this whole thing... Well, if you're plugged in 0 for all the x's, you get 0. But yeah, if we plot these 3 points, one at 0, one at 3, one at negative 4, we combine that with an end behavior that goes up in both directions, we should be able to draw a shape. And watch this. Kind of going on by like just drawing like almost like through a thread. Huh. There's like a problem here. You know, this doesn't connect up. So try that again. Maybe if I draw from the other side. Oh, it still doesn't connect up. If I'm only to have these 3 x-intercepts, and yet an end behavior that goes up to the right and left, it doesn't make sense that, you know, that it should. It just doesn't. It doesn't add up. It doesn't seem to connect. The lines don't seem to connect up. So what happens? And this is one more little detail, but since I'm gonna erase this so you can see it better. Since this particular 0, the x minus 3 squared, since it is squared, we call this a repeated 0. In other words, that's very hard to spell with this, but this plus 3 counts as a repeated 0, which means that at this spot right here, I'm going to expect the graph to do a different kind of shape. Instead of crossing like it does here and here, it's going to touch. It's going to bounce off of the x-axis and continue on. So that's the kind of shape I'll expect. It'll come in, bounce off, and then it'll go about its business of crossing and crossing. So something more like this is what the shape would be. And as you'll see, that lines up now. It actually does have the proper shape. Hopefully this helps. There's obviously more, and these ones you'd have to actually factor by some more extraordinary means, like using the plus or minus p or q thing in polynomial division. If you got questions on that, let me know. Hopefully this at least gets you started. This gives you an idea of what to do.